Welcome back, everybody. So we're going to look at the second set of notes related to polar equations and graphs. So for this, we're going to focus on symmetries, which we talked about at the end of the last video. So what we're going to look at is kind of reviewing the three different types of symmetry that are going to be most common for our polar equations and graphs. So that's going to be symmetry about the polar axis, or what we think of as the x-axis in rectangular coordinates. The line theta equals pi over 2, which is like the y-axis. And then the pole, which is just the origin. So symmetry about the origin. And because these are equations, not functions, right? We don't think of them as functions, obviously, because we don't have this uniqueness of outputs and inputs. These are just equations, so we can have all three types of symmetries for our equations. So we'll start with the polar axis symmetry. So that is going to be taking this value r theta and reflecting it about the x-axis. So this point is going to be on the same curve, so you can imagine some polar curve here that has this symmetry. Maybe it's a circle, maybe it's a cardioid. And so if we don't know what the graph quite looks like, right, is there a way we can test for this symmetry? And the tricky part of this that it differs from finding symmetries with, say, a function in rectangular coordinates is, again, we don't have uniqueness in points because we've got coterminal angles and different ways of representing points with positive r values, positive theta values, negative r values, negative theta values. So we have to check two different ways. So the first way is going to be using positive r, so measuring the radius to the right, and the other is going to be using negative r, or measuring the radius to the left, to start and then rotating a particular way. So for each one of these, it's going to be the same starting point, which is we're going to let r and negative r be the r values for our given coordinate. And we're going to need to figure out, well, what value should the angle be that's going to map to that same point? So we can see here, obviously, that if we measure out r units, we can just rotate in reverse to get theta. So this coordinate would be equivalent to r comma negative theta. Or if we start out over on this side with negative r, we can rotate from pi to that point. So that is going to be pi minus theta, because we're rotating in the counterclockwise direction, so it would be a positive angle measure. So it's just going to be pi minus theta. And so what that means is if I have some polar equation, so r is equal to some equation in terms of theta, then if I take f of negative theta, I will get r. Or if I take f of pi minus theta, I will get r. And so, this could be maybe 3 cosine theta would be an example of the polar axis symmetry. So this would be a circle with diameter 3. And so this graph would work because 3 times cosine negative theta is equal to 3 cosine theta by the even symmetry of the cosine function. So in general, what we're going to look for is those given coordinates, and we can think of them kind of like a function, or as a function if we want to, or just as a relation in terms of theta. All right, so for our second symmetry, now we've got symmetry about theta equals pi over 2. Oops. So we're going to, again, put our coordinates as r comma something, negative r comma something. So if we do it as r, we can measure out r here, and then we'll rotate over. We can see that we need to go almost pi, but not quite pi. So this is going to be pi minus theta again. So similar to what we did for the second pairing, only r is positive now. And then for negative r, well, I just need to rotate clockwise here to get to that point, so that would be negative theta. So r comma negative theta. So an example of this would be r is equal to 3 sine theta. And so if we did our check here, we would substitute maybe r3 sine pi minus theta. And if we do that calculation, we'll get sine of pi cosine theta minus sine theta cosine pi. And what we'll notice here is that we're using this trig identity for the angle sum or difference of sine. And sine of pi is just going to be 0. So what we're left with is this negative sine theta cosine pi, but cosine pi is negative 1. So then we end up with r is equal to 3 sine theta. And what that means is that these are equivalent expressions, which means they're on the same curve. So again, our starting point is to do the substitution. So in this case, r remains the same, but the angle becomes pi minus theta. But what we notice is that we still get the same calculation out at the end as our original given equation. All right. And then finally, we've got our symmetry about the pole. So we've got r comma theta, again, in the first quadrant, and then we've got r comma something, negative r comma something here. So if we start with positive r, we can rotate around this way, or in reverse. So there's kind of two different ways you can think about this. The way we're going to choose is actually rotating all the way from standard position in the positive direction, which is going to be pi plus theta. Put that in red. And then if we're measuring from negative r, we can see we can just rotate theta degrees from negative r. So this is going to be negative r positive theta. So if we're looking at this type of equation where we might have this symmetry, it might be maybe a rose curve of some kind. So we'll kind of see one come up here where we've got kind of maybe a multiple angle measure. And the key idea again is that we must check both. So if it fails for one and works for the other, we have that symmetry. If it doesn't work for both, then we do not have the symmetry. And again, these two symmetry checks are because of our non-uniqueness of points in polar coordinates. All right, so I've kind of made a little table sort of section here for us for each one of these equations. And so we're not going to do all of them together, but we'll pick a couple just kind of as examples to work through, and then I'll let you check the completed notes online. So we already discussed 3 cosine of theta. So why don't we jump to 3 sine of theta, which we also discussed, is also a circle. And we'll focus on each one of the types of symmetries and showing how it is or is not going to be the case. So for our polar axis symmetry, again, that is our x-axis symmetry. That means we're going to be checking r negative theta or negative r pi minus theta. So we're going to be checking either one of those. So we'll go ahead and start just above here. So we'll have r equals 3 sine negative theta. But obviously, that means that r is equal to negative 3 sine theta, which is not our original equation. So that symmetry check fails. And then if we go to negative r pi minus theta, so we'll have negative r 3 sine pi minus theta. From our previous work, we know that sine of pi minus theta is the same as sine of theta. So I'll leave that part off, but you could again write out that difference identity. We'll also see that it does not work. So there is no polar axis symmetry. Theta equals pi over 2. We already showed above that that will work if we use r comma pi minus theta. And again, that is because sine of pi minus theta is the same as sine of theta. And then finally, we can look at the symmetry about the pole. So that's going to be negative r theta, or r comma pi plus theta. And so the first check is pretty easy. Negative r equals 3 sine theta is not the same as r equals 3 sine theta. So that's a very quick check. And then for pi plus theta, we'll have r is equal to 3 sine pi plus theta. And if we use the identity here, we'll see that that's going to equal negative sine theta. So we get r equals negative 3 sine theta, which is also false. Or is also not equivalent to the same polar graph that we started with. So really, this is what we're going to be doing for each case here. And we're going to start with, again, some common ones that we know, and then we'll look at some other examples. And really where it's going to be most useful is with graphs that are maybe a little bit harder to graph themselves. But we'll kind of look at the kind of known graphs here to start. So we have the circle equations here for 1 and 2. For 3 and 4, we've got cardioids. Right? So the coefficients are equal to each other. So this is going to be a heart-shaped graph. So we're going to get that sort of heart-shaped graph to us. So looks like we should get some specific symmetries here. But we want to prove it. So we'll start with, or we'll do number 4 and we'll skip number 3. So for the polar axis, and note you can have multiple symmetries. So you can have more than one symmetry. So for the polar axis, we'll do r is equal to 2 plus 2 cosine negative theta, which obviously gives us our original equation. So definitely has polar axis symmetry. And then if we check theta equals pi over 2, so that's going to be r pi minus theta, or negative r negative theta. So we'll have r is equal to 2 plus 2 cosine pi minus theta. But cosine of pi minus theta, which again you can write out to verify, which is cosine pi cosine theta minus sine pi sine theta. So again, sine pi is just 0, so that's going to cancel out. And then cosine pi is negative 1, so we get minus cosine theta. So this becomes negative 2 cosine theta. So that doesn't work. And then negative r equals 2 plus 2 cosine negative theta. Well, that negative r doesn't change, even though we can change the cosine. So still not the same equation. So this is going to be no polar axis, or no symmetry about pi theta equals pi over 2. And finally, symmetry about the pole. So that's going to be r pi plus theta. So we'll note cosine of pi. Oh, sorry, this should be plus. And cosine of pi plus theta is actually the same as cosine pi minus theta. Because we get the same expression but with minus. But because it's at pi, the sign doesn't matter. because sine will be 0 either way at pi. So now that's just 0, and we get the same expression to start. So we kind of already know this is going to fail, because we're going to end up with the same equation that we got here. Now for the negative r check, that'll be negative r theta. That also kind of immediately fails, because we have negative r is equal to 2 plus 2 cosine theta, which is not equal to our original given equation. So on the next page, we've got a couple of different graphs. We've got a Rose curve, a lemniscate, we've got r equals theta and